It's the new, improved Pico-Hydro system. Woohoo! Here we go. The water's on. Obviously. Here are the elements of the Pico-Hydro system, and you can generalize this to any hydropower system, really. Got some stream, build a dam, create a reservoir. Here's it. This is sort of a perspective sketch, and this is the reservoir in cross section. Got an intake pipe, some fat pipe with screened holes. A little dam. And one more parting shot of our little pond here.
As you can see, there's a lot of little half-inch holes drilled about a half-inch on center. So there's about a half-inch gap between each hole all the way along this pipe. And then it's wrapped 2 or 3 times with just some aluminum screen. And then duct taped at the end and hose clamps. And then there's what they call a Fernco style fitting, which is 3-inch. This is 3-inch pipe with a 3-inch cap, and then a Fernco 3-inch to 2-inch fitting at the end, which is nice because it makes it flexible. So you can pick it up out of the water, clean it off if you have to occasionally, move it around, redistribute it, and so on. So obviously a little bit of sediment and whatnot's going to get in there, but it seems to do a pretty good job of creating a fairly clean water source.
And then the penstock, which is simply the pipe, or whatever leads the water down the hill. And here, just drawn it as a red line. Down the hill to a jet, which I haven't drawn because it's very small, to turn your turbine. The jet turns the turbine, turns the shaft, turns the coils in the alternator, generates DC current. So here's your live wire and your ground. And we're using a permanent magnet alternator. And here's the new setup for the Pico-Hydro. We got our T, 2 Ys, and then PEX, the grass, and an adjustable aperture nozzle there. And then, rather than the homemade, we've got a real Pelton wheel now. And then I got the bucket. I got steel frames for everything.
Alright, we've got a grounding rod pounded into the ground. Now we're going to run a ground wire from our alternator to the grounding rod. So we're using a 10 gauge THHN wire for our ground. So we've got the ground wire for our alternator, and the wire ran from the ground on our batteries, and we're going to hook both of those together to a common ground that we place near the alternator. Using, not really sure what this is, just a rebar ground connector. You go into Home Depot and tell them something like that, they'll show you something similar to this, which is what we're going to use. Just went ahead twisting our wires together. I'll just shove them in there, tighten them in, give them both a good little tug, make sure they're good and tight. And then we'll just hook it to the rebar ground. And voila. Now we can hook our wires up to our alternator. So before we had 2 instrument arrays hooked to the same alternator, but because of some noise issues using a common power supply, we decided we were going to build another alternator, or another Pico-Hydro generator to separate the two. So our power wire from both our battery boxes is still hooked in the same alternator. So I'm going to pull one of the power wires that run to the box off of this alternator and switch it over to that one. So here's our power wire to one of the boxes. We ran a 12 gauge THHN for our power wire and a 10 gauge for our ground. I'm going to go ahead and hook this power wire back up so we don't forget.
So here's my set of things to remember when you put it together your own system, if you're going to do it. Because it's not that hard. Fat pipe. Fat pipe means lower speeds in that pipe for the same amount of flow. And lower, that means less friction against the walls of the pipe, greater efficiency, less head loss in the pipe. That is, you know, if my intake is sitting up 20 meters higher than my nozzles, and I'm shooting out jets down here, I want that water going through there the lowest speed possible so I don't effectively have only 10 meters instead of that 20. So fat pipe as far as you can get, as close to your end point as possible, as feasible. Gradual bends, avoid 90-degree turns, hard turns, sudden turns. Well, we had a T, we're not going to replace it, but it's relatively large diameter, so it's probably not a big deal. But then Y splits so that we're not trying to make hard turns, because Ys have less head loss than Ts. And then coming off those Ts, reductions, I don't know how gradual they are, but then to PEX tubing that we can flex in a gradual bend to the nozzles themselves. After that last T, no more 90-degree turns, no more sudden turns, no more high curvatures, that is, sharp bends. Gradual reductions. When you're going from big to small diameter, because you've got to go to small diameter to get your nice fast jet to push your propeller. But sudden reductions, you know, stuff that goes like that. Right? That kind of sudden reduction where you've got water coming in here, going out there, gives you a big head loss. So avoid that. In fact, what's awesome is if your nozzles are tapered, right? So from the input of the nozzle to the little bit at the end where you want it to get small enough to have a high velocity jet, taper that, right? Smooth this out. Nozzles with variable aperture. We got some nozzles that just simply screw in and out. There's this little rubber sleeve in there. We got it from the same place that we got the turbines. That way we can tune it. If we're getting too much flow through there and we're getting the level of our reservoirs dropping, and we can hear that because we're getting that, you know, crackling in the pipes, which is air bubbles.
I'm not sure what that crackling noise is.
Narrow the nozzle down, reduce the flow to something manageable. Don't need as much power as you're getting, turn it down a little bit more so you're just, you know, reducing the suction on that uptake, that intake end, reducing the likelihood that mud's going to glom onto it and lodge there and clog up your intake. Aimable nozzles. Wow, right? Our first system, everything was glued into place. Now we glued it out in the field, but once it's glued, once that glue is set, you can't change it. The nozzle's pointed where it's going to point, and you're stuck with it. If you miss, so here's a Pelton wheel. It matters where the jet hits on here. If you hit too far towards the inside, it's less efficient. If you hit too far to the outside, it's less efficient. Geez, you know, if you shoot too far out, you don't even hit the thing at all because you've got this big slot. So you want to hit 2/5 of the way out from you want the center of your jet to be 2/5 of the way out from the inner side of the cup. Now that's a bit tricky to do. You know, you're probably not going to be there able to get in there with a good ruler and figure it out exactly as the water's flying all over the place, right? And then you've got this sort of almost blade-like fin that cuts that cup in half and cuts the jet in half. And so you can see, is the water spraying off? Is it coming off into equal sprays? And being able to fine-tune that is really nice. We've got a system, it's pretty simple, bolt, washer, you know, aim the thing.
John's trying to get the jets aimed just right. Unlike the former system, we've actually got a way to adjust the jet.
So now you're halfway in between, the same stream on top of the on the bottom.
Beautiful. Yeah, it's perfect. You see the spray coming off, and it's symmetric top and bottom, which is exactly what you want. You want the jet to be split right in two evenly.
Finally, high voltage. High voltage, I should write that 3 times. High voltage, high voltage, high voltage. The higher the voltage, for the same power, higher voltage means lower current, much less resistance, faster spinning wheel. I mean, these alternators, they want to spin at like 1,000 RPM. I don't even know how to measure that, but I do know that we're slow, you know, because we're just at these low voltages, drawing relatively high currents, a lot of resistance on the wheel, and, you know, it's just not awesome. So higher voltage, always with the alternator itself, always higher voltage gets you better efficiency. And generally higher voltage means somewhat less current, and less current means less resistance, and less resistance on that wheel means faster wheel. And a faster wheel, in our case, with our jet velocities, means greater efficiency. And that's probably going to be true. I mean, you know, this is not some ultra special system, right? All we've got is a 2-inch PVC pipe going up the hill, sucking in water, and letting it out at the bottom. This is not rocket science. Well, maybe it is sort of like rocket science. We got our jets, right? Jet science. But yeah, so it's not some weird special system. It's high head, low flow. And, you know, typically you're drawing current, you know, that puts resistance on that wheel. You're going to have trouble getting that wheel to spin fast enough to get the best efficiency. So high voltage to the extent that you can. You know, maybe you're okay with low efficiency. If all you really need is whatever power you're able to eke out of it, then that's cool. If you'd like to have some headroom, if you'd like to charge your batteries faster, for example, more power is always better. And the higher the voltage, the more power.
Open circuit voltage on the one John's lying on top of right now was about 70 volts. The other one was about 90 volts. So right now they're hooked up to batteries, 12-volt batteries in parallel, so they're basically pinned at 12 volts. And at that low a voltage, the current's high enough that it gives a lot more resistance to spinning. Doubling the voltage would get us more than double the power. But our charge controller that we have right now only works at 12 volts. So if we're going to run at higher voltage, we'd have to either get some voltage converters or get a different charge controller. Charge controllers run about $100. I don't know why they're so expensive, but they run about $100. So it might be we might be better off rigging, getting somebody to make us a relatively cheap voltage converter. So we've been experimenting with stacking the batteries, so to speak. That is, normally these are hooked up in parallel, but right now they're hooked up in series. That is, charge comes in over here, then negative terminal hooked to positive terminal, negative terminal hooked to positive terminal, negative terminal hooked to positive terminal. So before, when we had them all in parallel, we're getting about 1.5 amps and at about 12 volts, which is about 18 watts. Hooked up in series like this, the open circuit voltage was about 61 volts. Once I put the circuit breaker in, it was at 51 volts, 0.95 amps. So roughly 50 watts. So quite a gain in efficiency. At 3 batteries, we had about 40 watts, I believe. So we didn't get quite as big a bang going to 4 batteries. And that's, I think, because the efficiency curve for the generator starts to level off at some point. Yeah, we go from 18 watts to 50 watts simply by operating at higher voltage.
Here's another important do. More surface area on your intake is better. We started off with an intake manifold, a single pipe, maybe looked something like this, say about a 3-inch PVC with holes cut in it and then screening all around that. We just found that was clogging up with whatever was floating in the water really easily. We then went to something sort of like this, where we cut long slits all the way down the pipe. And here's a sideways view. We can see the screening here. Now, what happens, that has more surface area on the table, on the workbench, but when you put it in, you start pulling flow through it, and you start getting a bit of stuff clogged on there and whatever, it sucks in. The lack of structural support decreases your surface area because those slat spaces then give and shrink up. And so then again, you've decreased your surface area, more likely to get stuff clogging there, glomming onto that screen with the high suction of the flow pulling it against it. So we went with, I forget whether some kind of steel ring or whatever, but it doesn't really matter. It could be another PVC, even the same size PVC, because it's so flexible you could fit it in there. That is, the slats are so flexible to give. So some support in there then keeps it from sucking in, maintains this large surface area. Then you have less suction on each little slot in the screen, and each little hole in the screen, right? You're less likely to hold mud and twigs and just detritus against that screen, more likely to keep the flow going. Now, currently we've got one of each. We've got one of this and one of this, and we've made a deeper pond. We started off, say, about 2 sandbags thick and then made it more like 3. We've kind of fiddled with the flow to keep a bit of swift flow going through there so that it doesn't make a too stagnant pool for lots of mud to settle out. Initially, with just this in pretty bad weather, admittedly, we only had, say, 10 days of uptime. But before the pond got filled with mud, before this got covered with mud and cut off the flow to our hydro generator. Now with one of each, and with the supports in here and a deeper pond, and maybe, the weather's been different too, so it's hard to say, but we've been up for more than 30 days without any maintenance, any attention to that pond. So more intake surface is better. I might also put up here deeper pond, but I think the more intake surface is probably the more important thing.
Here's our new pipe system, our new manifold, intake manifold, that I've dug out a lot of sediment from underneath to fill bags that I've filled. So basically dredging and filling here. And we've got our original pipe, which is a 3-inch pipe, 3-inch PVC with holes drilled in it and screen wrapped around that. And our new pipe, which is 3-inch PVC with slots cut all the way out of the sides and screened around that. So we've got a lot more surface area, slower velocity going into the pipes, less required of any particular spot in the pipe, and less tendency to suck debris onto the screens that will then clog the screens.
Final do. Faster jet. Prefer faster jet to more flow to increase your power. Remember, the efficiency is increasing with power input, right? More power in the greater efficiency. Duh, right? Well, I mean, that's awesome. How do I get more power? Only got so much, right? Well, yeah, you've got a certain potential energy. But, you know, maybe you open up your nozzles, allow more flow through. That could give you more power. Well, power increases with velocity squared and flow rate. No square on flow rate, right? So prefer faster to more, right? Prefer faster flow to just more flow. More flow will maybe get you more power. On the other hand, more flow might, you open up your nozzles all the way and it's not very fast. You may actually lose power that way. So best efficiency, best bang for the buck is limit the flow if you need to, get that velocity up. So I know, efficiency curves, voltage, power input, blah, blah, blah. What's the upshot? All right, so if I've got two efficiency curves, I know they go like this. That is, they are steep at low values of voltage, low values of speed that I'm out here. Okay, if this is efficiency here, I know I'm falling off the steep end of both of those things. So, what do? I measure my open circuit voltage. I could measure my short circuit current. But the open circuit voltage is the real thing. That gives you the upper limit of the possible voltages that you could use. So, and then you know, well, there's nowhere to go but up here, right? Higher the voltage I can let the thing sit at, the greater my efficiency, especially when I'm out in this steep part. And here, I know I'm also out here where my wheel has too much resistance on it. It's not turning very fast relative to the speed of the water hitting the propeller blades. So, and I'm on this steep part of the curve. Actually, this is more like an upside down parabola like this. And I know I'm out here. So, and I'm, you know, on the bad side, I'm sort of falling off of both of these curves. But if I climb up a bit, I'm going to get quite a bit more efficiency. And that's what we're seeing just from, okay, let's try putting two batteries together. So we've got 24 nominal volts. Let's try putting three batteries together. So we got 36 nominal volts. Let's put 48, etc. We've gone to 48, and it keeps giving us more power. And so that's the recipe, essentially. You know, just know that you're on these steep curves, and when you're at 12 volts, you're way down here. So getting it higher is all good. If you're at 12 volts, you're probably at pretty high current relative to that. Your resistance is high because resistance goes as the current squared. So if you can get the current to be smaller, that's awesome. Short thing is stack your batteries and then figure out how to deal with the voltage that you're getting. That's kind of the thing, is then the problem we're having is how do our system doesn't work at 50 volts. So we're going to have to get voltage converters if we want to utilize that power. Right now we're ticking along okay, right? We don't actually need all that power that we could be getting. But it'd be nice to have an inverter out there, plug in a laptop, plug in an oscilloscope, plug in a soldering iron so we could do electronics work on site. Because the lab is one thing, the field is another.